Hypermetropia, let us see the numericals which will help us understand hypermetropia in a better way. Looking at the first question, the question says the near point of a hypermetric eye is 1 meter. Now students, what do we understand from this? It says that if image is formed till 1 meter, this person is able to see clearly. So exactly what data is given to us is nothing but the image distance. So here you can see diverging rays hit the lens and from there they are supposed to go on the retina. So image distance is 1 meter. Further, what is the nature and power of the lens required to correct this defect? Assume that the near point of the normal eye is 25 centimeter. Now students, the near point for a normal eye is 25 centimeter. That means if object is kept at 25 centimeter for this person, it should be visible clearly. So what is given is object distance 25 centimeter. As it is to the left, we take it as minus. Now what are we supposed to find in this numerical? We are supposed to find the nature and the power of the lens. So let's start with the sum. Firstly, object distance given by u, and object distance in this case is minus 25 centimeter. Further, image distance. The image distance v is equal to 1 meter and we take it as minus because image is formed to the left of the lens. Now this minus 1 meter can be written as minus 100 centimeter. Now what are we supposed to find? We have to find the nature and power of lens. Now to find nature and power of the lens, the first formula we require is 1 upon v minus 1 upon u is equal to 1 upon f. That is the lens formula. And the second formula we require is the formula for power, and power p is equal to 1 upon f, where focal length should always be in meter. Now let us start with this numerical and apply the lens formula. 1 upon v. Now we know v is minus 100, so 1 upon minus 100 minus 1 upon u. Now we know u is 25, so it will be 1 upon minus 25 is equal to 1 upon f. Now minus 1 upon minus 25 becomes plus, so this equation turns into minus 1 upon 100 plus 1 upon 25 is equal to 1 upon f. Now going further students, we take the LCM, and in this case the LCM is 100, so it will be minus 1 plus 4 in the numerator upon 100, and this is equal to 1 upon f. So therefore students, from this the next equation is 3 upon 100 is equal to 1 upon f. Therefore f is equal to 100 upon 3. So we have this 100 upon 3, and 100 upon 3 is nothing but equal to 33.3 centimeter. Now here we can see the focal length is positive. Now as the focal length is positive, the lens which this person should use has to be a convex lens. So therefore students, we have understood the focal length. Now let's go to the second part and find the power. Now we know the formula for power p is equal to 1 upon f, where focal length is in meters. So therefore it will be 1 upon 0.33 because we have to convert 33.3 centimeter into meters. Now 1 upon 0.33 multiplying and dividing by 100 is equal to 100 upon 33, and 100 upon 33 is plus 3.0 diopters. So students, the answer for this numerical, the power is 3 diopters. So let's understand what we did in this numerical. In this numerical, what we have done is we have given this person a convex lens, because a convex lens which converges the rays, and after converging the rays go and fall on the retina. The convex lens this person should wear is a lens having focal length 33.3 centimeter and power plus 3 diopters. So students, this was the first numerical to understand hypermetropia. The final statement, of course, a convex lens of focal length 33.3 centimeters required, and the power of the lens is plus 3 diopters. So students, let us see the next numerical. The question says an eye has a near point distance of 0.75 meter. What sort of lens would be needed to reduce the near point distance to 0.25 meter? Also calculate the power of the lens required in this eye. Is it long-sighted or is it short-sighted? So students, the first thing is an eye has a near point distance of 0.75 meter. That means till 0.75 meter, that is 75 centimeter, if image is formed, it can be seen clearly. So the first data which is provided to us is nothing but the image distance, which is 0.75 meter. Now further it says, what sort of lens would be needed to reduce the near point to 0.25 meter? That means the object distance is 0.25 meter. Now students, what are we supposed to find? The nature and the power of the lens. Now to find this, let's start with the numerical again. Here, first thing given, image distance V is equal to 0.75 meter. We take it as negative because image is formed to the left of the lens. Further, object distance U, and object distance U is equal to 0.25 meter, again to the left of the lens because object is always placed to the left of the lens. Now what are you supposed to find? You have to find the nature and power of lens. To find nature and power, let's start with the formula. The first formula is 1 upon V minus 1 upon U is equal to 1 upon F. And the second formula is the formula of power, and power is equal to 1 upon F, that is the focal length. Now let's go to the solution. In the first part of the solution, using the lens formula, I get 1 upon minus 0.75 minus 1 upon U, and that is 1 upon minus 0.25 is equal to 1 upon F. Now again, minus minus cancels. So I get 1 upon minus 0.75 plus 1 upon 0.25 is equal to 1 upon F. Now further students, let's simplify this further. On simplifying it further, I get LCM 0.75, and in the numerator, it will be minus 1 plus 3, and that is equal to 1 upon F. So therefore students, this will be 2 upon 0.75 is equal to 1 upon F. Now doing invertendo, I get F is equal to 0.75 upon 2, and therefore the answer is F is equal to 0.375 meter. Now once again, the focal length is positive, so therefore it is convex lens. Now, so therefore the answer is the convex lens of focal length 0.375 meter is required to correct the defect. Now let's go to the second part and find the power. The power P is equal to 1 upon F, and we have found the focal length. The focal length is 1 upon 0.375. So 1 upon 0.375 is nothing but multiplying and dividing by 1000. I get 1000 upon 375, and therefore the answer is 2.67 diopter. So students, what is our understanding of this numerical? In this numerical, we understand that a convex lens is used to correct the defect because it will converge the rays, and again from the eye lens the rays get converged and the light falls on the retina. The power of this convex lens should be 2.67, and the focal length, as we know, should be 0.375 meter. So therefore, this students was the second numerical of hypermetropia. Thank you.